Okay, next we want to talk a little bit more about OpenCL while we're looking at these hardware architectures of different processors. Global memory. Global memory maps to cache hierarchy. If we look at the GPU, in this example, it's AMD GPU, but it doesn't matter. Any other GPUs that you can find, pretty much has the same or similar organization. Global memory is what you see here. This is kind of the biggest memory subsystem to the GPU. Usually it's outside the GPU chip. And this memory stores all the data that you want to store before and after computation. Constant memory is a special region that's sometimes a part of the global memory. I want to mention that the way we draw this diagram is this kernel represents the OpenCL kernel, and this kernel is has nothing to do with OS kernel. If you learned the kernel in the OS operating system class, this kernel has nothing to do with the OS kernel. This kernel is kind of the way that you design a data parallel program within OpenCL framework. This is the program you're going to write. And on the right side here, this is an example of a processor. We just use AMD GPU as an example. You can replace it with other processor architecture that supports OpenCL. So what we see here is the global memory is the memory shared by all the computing units, and mapped to a GPU system. This is the kind of the global GPU memory. Constant memory is a part of the global memory. You can use the constant memory to store those constants, and depends on the actual vendor of the memory. This could be a special region, but it intends to store the constant that will be useful in the computation. And these constant memory should be optimized for read operations, because you don't expect to write them during runtime. Local memory. Local memory is here. Now I want to just say a few words about this dashed box here. We call it work group 0, work group 1, work group n. We will know more about this. We'll have a lot of examples. But the concept is to divide your computation based on the data, and each work group performs a subset of the computation, a subset of data. So this work group will be put onto a processor core. As we see on the right side, this is the vector processor. It doesn't matter. You can think about this as a GPU core. So a work group will be mapped to a GPU core, and this local memory, which is local to a work group, will be mapped to a local data share on one of the cores. Now when we say local, we really mean that it's local to within the work group. So the data that you store in this local memory within work group 0 will be invisible to the compute units in work group 1. And that's why we use this local data share on this vector processor 0, because this piece of memory, the data that's stored here, are accessible to all the execution units within this processor. And then we have work item, which is within this work group. We have many work items, and these work items will be the actual computation that you want to perform and each work item has its own private data, so that we have a private memory. Private memory, if we map these to the actual hardware, these are the register files. So within the cores. Okay, so I think this is if I say, if I pick a few slides, this is probably one of the important slides you need to pay attention to in today's class. Here we show in more detail how the OpenCL memory is mapped to AMD GPU. This is the compute device. You can think about this as the whole GPU. And within the device, you have some kind of command processor, which you can ignore for now. This really handles the scheduling of the instructions to these, reading and scheduling instructions to these compute units. And this compute unit has level 1 cache, and that shares some kind of level 2 cache, then connect to the global memory, the GPU memory here. And this memory, the GPU memory, is the global memory in a context of OpenCL. The compute unit is equivalent to a core, and in this compute unit, you have multiple SMD lanes. In this case, we have 4 lanes. So we can think about this, a smaller piece of function you can execute instructions, and they share local data share. So this is the local memory we're talking about. Now, if we zoom into this SMD unit, this is SMD lane, and this one does the actual computation. So it has private register file, and they call it vector GPRs. And this is the private memory in the context of OpenCL. So we have 3 levels of memory. Global memory, which is typically off-chip. Some local memory, which is shared by the little function units. And then we have the function units, the hardware, which does the computation, and that has its own register files. So that's the private memory. So we talk about the concept of kernel briefly. We know kernel is kind of a program you expect to provide to OpenCL framework to implement the algorithm you want to implement. The ideal kernel for a GPU, we would like to have thousands of independent pieces of work. We really want to, in this kernel, to break your computation task into small pieces based on the piece of data. We want to break them into as many as possible, as long as there's no dependencies. We want to have thousands of these pieces of work in order to use all available compute units. As we know, especially modern GPUs, you have a lot of cores, thousands of cores. And you would like to make as many of these cores busy, and also with large number of independent pieces of work, you can allow the hardware to do context switching to hide memory access latency. Also, we want a kernel to be amenable to instruction stream sharing. We would like to have the same instruction stream shared by all different cores. In this way, we can prevent divergence between the work items. Also, we hope to have high arithmetic intensity. We talked about arithmetic intensity. Essentially, it's the ratio between your computation and the memory access. We would like this, math operations to memory access as high as possible, so that it's not limited by memory bandwidth.